Now, it's time to clarify a point which I have never seen well explained in books. Hello guys, in this video we're talking about kinetics. But before that, I would like to announce that you can find the article about this video on my website, which is www.operachem.com. You can find the link for this website in the description box. But now, let's talk about kinetics in chemistry. First of all, what is kinetics? Kinetics studies the rate of chemical reactions. Why kinetics is important? Because with kinetics, we will have information about the rate of a chemical reaction, which is important if you have a company and you synthesize product. In that case, it's important to have fast reaction. So you will hire chemists in order to speed up your reaction, speed up the production of your substances. You don't want slow reaction. That's the reason why kinetics is important. That's the reason why, as a chemist, you have to study that. But there is also another reason. With kinetics, we can understand the reaction mechanism. That means that we can know exactly all the steps which are involved in this reaction. So we can know exactly how the reaction occurs. However, we will cover reaction mechanism in our next video about kinetics. In this video, we are going to learn the definition of speed in chemistry and the kinetic law. So let's start from the beginning. What is the definition of speed in chemistry? If you remember something about your physics lectures, you will know that in physics, speed is always the change of some property over the time. So the same will be in chemistry. But what is this property in chemistry that changes over time? The answer can only be the concentration. Since during the course of a reaction, the concentration of reagents decreases while the concentration of product increases. So we can write this equation, which means that in chemistry, the speed is the variation of concentration of reagents or products over the time. In this equation, the concentration is expressed in molarity. I would like to remind you that molarity is mole of your solute divided by the volume of your solution. Now, the concentration can be the concentration of reagent or the concentration of products. This means that we can define the speed in chemistry using both concentration of reagent or concentration of products. But as you can see from this last equation you see on your screen, there is a minus sign when we are talking about reagents, whereas there is a plus sign when we are talking about products. Why there is this difference? Because if we are dealing with reagents, let's say that at the beginning of our reaction we have 50 mole over liter of our reagent. After reaction, what is left is 20 mole over liter. Now, if we have to calculate the rate based on these reagents, we will have to make the difference between 20, which is our last concentration, then we have to do minus the concentration at the beginning, which is 50, and as you can see, it's minus 13, so it's negative results. So now you have to understand the psychology of chemists. Chemists doesn't like minus sign. So what they've done? They have thought to their students all over the world that this minus sign is not good, you have to erase it, because it has no sense for the speed of reaction in chemistry. So all the chemists now, we have to remember, because of this psychological status of some chemists in the past, now we have to always make our speed positive. So in order to make our speed positive, we have to add minus sign when we are calculating the speed using reagents. Okay, it's a convention due to the hate of chemists for the minus sign. Whereas, as you may know, in physics there is no problem if you have a negative speeds, because negative speeds just mean that you're going in the opposite direction than the positive speeds. But you know, chemists are chemists with their problems. But now, let's take an example just to understand better. So let's take this reaction. Let's suppose that we have calculated the concentration of bromine at the beginning, which was 3 mol over liter, and then after 200 seconds. And this concentration was 1.5 over liter. So now the consumption rate of bromine will be given by our first equation, so which is this one. So let's just put data on it. So we have to do 1.5 minus 3 divided by the range of time, which is 200 seconds. So as you can see, we gain a negative charge, but as I told you, negative charge chemist doesn't like that, so make that positive by adding negative charge at the beginning of your equation. So far we have, I hope, understood that speed in chemistry depends upon the concentration. But now let's do a step further. Let's see how to write the speed for a generic equations. So let's take a generic equation as this one. The reaction rate will be expressed with this equation here. So as you can see from this equation, we have introduced now another element, which is the stoichiometric coefficient. So why we have to divide by the stoichiometric coefficient? So the reason is the same as in the case of weight ratios in chemical reaction. For a generic reactions, I can write also this equation here. As you can see, the moles of my reagents and product are all divided by their own stoichiometric coefficients. Such an equation helps us to calculate the mole of one reagent starting from the other reagents, or to calculate the moles of product knowing the moles of the reagent. For instance, if I want to know the moles of my compound C, I can calculate that by the mole of my compound A, dividing the mole of my compound A by A, the stoichiometric coefficients of A, and then multiply it by the stoichiometric coefficient of C. So these are the basics of weight ratios in chemical reaction. I hope you remember that. Now, why I talk back those old equations? The reason is that these two equations together, they are actually related. Because since the rate in chemistry depends on concentration, which in turn depends on moles involved, and since moles depend on stoichiometric coefficient, then also my equation about rate will depend on stoichiometric coefficient. That's the reason why I hope this can help you to remember better both of these equations, which can help for your future as chemist. Now, it's time to clarify a point which I have never seen well explained in books. The point is the difference between reaction rate and the rate of consumption or formation. Are they the same thing? Let's see that. No, they are not. Reaction rate is independent of the stoichiometric coefficients and is the same for all the chemical species. Whereas rate of formation or consumption depends on the stoichiometric coefficients. But let's do an example, because I know you didn't get it. Let's take this reaction. The ammonia formation rate has been reported as 1.15 mol over liters an hour. We have to calculate the rate as function of hydrogen, as function of nitrogen, and the rate of the reaction. So we will learn the difference. Let's start from the rate of hydrogen consumption. As you can see, using our generic equation you have just seen, we have to take into account the stoichiometric coefficient. So we have the rate of ammonia formation, but we have to think that for each 2 moles of ammonia, 3 moles of hydrogen are consumed. So we obtain that the rate of formation of hydrogen will be given by the rate of formation of ammonia, which is 1.15, divided by the stoichiometric coefficient of ammonia, which is 2, and multiplied by 3, which is the stoichiometric coefficient of hydrogen. The result is 1.0 0.72. Let's do the same for nitrogen. The relationship between ammonia and nitrogen is 2 mole of ammonia each 1 mole of nitrogen. So we have to write that the rate of nitrogen consumption is 1.15 again divided by simply 2, because the coefficient of nitrogen is just 1, so it's useless to consider that. So the result is 0.575. Now, what is the reaction rate? Because so far we have calculated the rate of formation or rate of consumption, but we do not know the rate of reaction, which, as I told you, is something different. How we can calculate that? The reaction rate should be similar for all our reactants, okay? So we have to divide the rate of formation or the rate of consumption for the stoichiometric coefficient of that reagent. So it's actually what is written in our generic equation, where actually there is the speed of the reaction. So simply, in our example, we can take the reaction formation of ammonia and simply divide it by the stoichiometric coefficient of ammonia, so by 2. The result will be 0.575 mole over liter and hours. So this is our reaction rate, but I could do the same using the formation rate of hydrogen or the formation rate of nitrogen. For instance, let's take the formation rate of hydrogen, we have calculated it before, divided it by the stoichiometric coefficient of hydrogen, and you will get the same results. And the same will be for nitrogen. Try it by yourself. So now let's move on. If we recall some basics of kinetics in physics, we can easily understand that our generic equation for reaction rate is valid only for constant rate. However, the rate of chemical reaction are not constant at all, but tend to slow down as the reactants are consumed. In fact, the typical trend of concentration of reagents or product over the time can be well displayed with these 2 graphs you see on your screen. Let's take the graph about the concentration of reagents over the time. As you can see, the concentration of a reagent decreases over the time rapidly at first and then more and more slowly. Similarly, the concentration of products increases rapidly at first and then more and more slowly. So to follow the speed trend, you can draw a line which is tangent for each point of your curves. So let's take a generic point. Let's draw our tangent for this point. Now, as you may know from your math studies, the angular coefficient of this line is actually the slope of this line, and the slope of this line is, in this case, the rate of our graph about concentration versus time. So when you have this kind of graphs, the tangent in each point will determine the rate in that point. It's what we call in maths derivative. In the case of reagents, the slope will be negative. The line leans on the left, while for products it will be positive. The line leans to the right. So to know the rate for all our curve, we need to draw a tangent for each of our points. But this concept in maths is equivalent to the concept of first derivative. Therefore, we can define the instantaneous rate of a chemical reaction with this equation here, which is the derivative of the concentration of reagent or products over the time. So, for a generic reaction, the equation we have just seen will be turned into something similar we have seen before, but with the constant rate. So now for instantaneous rate, we will have this equation here with the derivative inside and the stoichiometric coefficients as we have seen before. It's actually the same, with the difference that for knowing instantaneous rates, you have to consider derivative and not a simple difference as it was before for our previous equation. So just add this step more, which is derivative, and it's done. You have now this equation, which is the fully definition of reaction rate in chemistry. So use this equation to tell to your professors the definition of chemical rate. You won't do mistake with this last equation. However, this equation is not of much practical use and is difficult to solve because it's a differential equation. So remember, this equation can be used as definition of rate, as I've already told to you, but from a practical point of view, chemists use the kinetic law. The kinetic law for talking about rate in chemistry. So what is kinetic law? Kinetic law is an equation that can only be found experimentally. So you can just find this equation in the lab. So if your professor asks you to tell you the kinetic law of a specific reaction, you have to tell him that you cannot know that because you haven't done the experiments, so you don't know the data from that experiments in order to know the kinetic law. So put in your mind that kinetic law, you can have that only with experiments in the lab. There is no other option. However, we can have an idea how the kinetic law can be with this kind of equation here. As you can see, in this equation, there is the letter K, which indicates a constant, and it's known as kinetic constant. And then you have concentration, again concentration. These concentrations are always expressed again in molarity, and these concentrations are generally the concentration of reagents. But in some case, in the kinetic law, there can be also the concentration of the product, but this is rare. As you can see, this concentration of reagents are actually elevated to these kind of numbers, x and y. What are x and y? These are numbers that are not the stoichiometric coefficient of the reaction, okay? They are not. They are numbers that have to be found experimentally, and they can be integer number or even rational number. So remember, they do not correspond to stoichiometric coefficient of the overall reaction, but actually they are the stoichiometric coefficient of only the rate determining step of the overall reaction. But the rate determining steps is something we will talk about in my next video when we will talk about mechanism. As you can see, the equation is written with ellipses because it's experimental and one cannot know how many and also which reagents will be part of the kinetic law. Let's take an example. Let's take the composition of acetaldehyde, which is this reaction here. As you can see, the kinetic law of this reaction was found in the lab and is this one. This kinetic law depends only on the concentration of acetaldehyde and depends also on this coefficient, which is 3/2. But this number has nothing to do with the stoichiometric coefficient of our balanced reaction, because there the stoichiometric coefficient is 1, so it's nothing to do with 3/2. That's because it's a value which was found experimentally. I don't want to repeat this again. Now, let's talk about some terms that chemists use related to the kinetics law. So chemists use these terms just to communicate each other when they speak about rates of reaction. So, for instance, the number x in our generic equation about kinetic law is identified as the reaction order of the chemical species A, while y identifies the chemical order of the chemical species B. The overall order of the reaction is given by the sum of all of these coefficients. So in the case that in our equation there is only A and B involved, the overall reaction order will be just x plus y. And that's it. But let's do an example as usual to understand better. Let's take this equation here. This is the kinetic law that was found for this equation. Now let's see the order for each species and the order for the overall reaction. Now it's pretty simple because the order for BrO3 minus and Br minus is simply 1, whereas the order for H plus is 2 And the overall order will be the sum of all of these order, so it will be 1 plus 1 plus 2, which is 4. So, as we have already seen, the order of reaction can be a fraction, as we have already seen for the decomposition of acetaldehyde, or can be an integer. However, there are also reactions which have 0 as order. It's quite unusual, but it can happen with heterogeneous reactions, such as the decomposition of phosphine on tungsten, while heating at higher pressure. This reaction has the following kinetic law, which is V equal to K. So it depends only upon the kinetic constant, and as I would like also to underline, the kinetic constant is independent on the concentration but depends only on the temperature. So if you change the temperature, that K will change. Remember that. As you can see, the overall order of this reaction is 0. So this is unusual, but it can happen, as I have already said, in some special cases as heterogeneous reaction. So for this video is everything. In the next video, we will see how in the lab we can gain the kinetic law, and also we will see the exercise you will find for sure during your examination about generic chemistry. So remember to go on my website, which is www.operachem.com.